So thank you everyone for attending my session today. It's called the 7 Deadly Sins of Streaming. My name is Yannis, and I work at Ververica as a staff streaming architect, and I'm also part of the Apache Fluss PPMC. Now I'm here today to share with you our work in terms of how we think about the future of stream and stream processing and our contributions in that space. And so I want to start this presentation to set the stage with this slide. And on top of it, it says Kafka is designed for streaming events and not for streaming analytics and AI. So what this means in practice is that Kafka excels to decouple systems and move events from point A to point B. However, it has been heavily used for for years for the analysis of data along with stream processors like Apache Fluss, as there were no other alternatives. However, this combination has resulted in a few challenges. Now, on the downside, in the down of the slide here, you can see my streaming guru. This is how I called it. And that has me holding my hand throughout my career in the streaming space. And there's a quote there, and this is something I have been using since day one. Everything is a stream. But what does this mean? Now, I'm a big advocate of streaming first approaches, and everything is a stream reflects that. However, this doesn't mean compromising historical data, which is something we're unable to do with Kafka-centric approaches. Everything around us happens in real time and can be thought of as events that occur at a particular point in time. Like right now, I'm talking to you, I'm interacting with you. But in order to be able to provide meaningful context and say the right things, I need to take all my historical context into account. So I'm able to provide something meaningful outputs. And this is how we also want our systems to reason about and be able to leverage both. So with that, I'm going to start with, over the years, what have we seen in streaming and the current status quo. And these are the 7 deadly sins we are going to see throughout this presentation. These are, and in my experience all these years, the main pain points we have been facing with Kafka-centric approaches. And everything starts with streaming data pipelines and Kafka being at the heart of it, and what we have been using all these years. And while we started introducing Kafka to decouple our systems and introduce decoupling of those systems, the first thing and the first question we had to add is how do I introduce schemas? Because at the end of the day, Kafka is there to just transmit raw bytes of data. And with that, we had this question, and we're like, okay, we're going to maintain an external schema registry to handle the schemas for us. And now, as the use cases starting to evolve and move beyond just produce-consume patterns, it was about, what about distributed processing? And there are many great frameworks out there. We have Spark structured streaming, we have Kafka streams, but Fling has grown to be a de facto gold standard for stream processing only due to this flexibility and the great stateful stream processing capabilities. Now, we had another question, but Kafka doesn't generate changelogs. And if you don't know what the changelog is, we'll dig into it in a bit. For now, suffice to say that it's just redundant storage costs. And because Kafka doesn't generate that changelog, Kafka needs to produce it and basically store a large amount of data on its state, only to write the results back to Kafka. So then we had another question. What if I need to perform key value lookups, like communicate with an external key value store or a cache? So we had to integrate other Fling processing jobs there, perform the lookups there, and do something like data enrichment. Now, the next question is like, what if I need to actually query my streams? Because Kafka is not queryable. So with that, we had to write the data and copy them again into an OLAP system, like Lakehouse, Starox, or Peanut, or other data warehouses. Now, keeping all data on Kafka is expensive. And also, we have the inability to query the data for correction or data analytics. And this has led, as an attempt to try and minimize costs with Kafka, to try and leverage the data lake. And these days is popular to use open table formats like Iceberg, Pymon, Delta, or Hoodie to offload the data from Kafka into your data lake and create a data lakehouse. But then, after you do the ingestion, you still need to do something with that data. And typically there, you have workload schedulers that schedule jobs typically in the hourly or daily intervals to calculate other layers on your data lake, like clean your data, enrich your data, and create aggregated tables that are ready to be served for business queries. And this is how we typically, all these years, have been differentiating between streaming and batch. But as you also know, that Flink is a unified batch and stream computing engine. But as an overall architecture, because systems don't live in isolations, we need to think about the high-level picture and how these things also play together. We basically have some kind of fragmented architectures and we require so many components. And this is also why historically, in my opinion, streaming has been perceived as something really expensive. Question, can anyone see any problems in this kind of approach we have been taking all these years? Or it's perfect. So if you think about it, we need to maintain an external schema registry. We have high networking data transfer costs because although, for example, we might be doing any kind of operations, we always need to transmit the whole payload for our data, even if it contains like hundreds or thousands of columns. We need to copy data from Kafka because it's not queryable. We need to copy it on Flink state. We need to copy it on the OLAP storage. We need to maintain an external key value store or a cache to perform key value lookups. We need to copy our data again into the data lake. And we need workflow schedulers only to recompute the same results again and again, when in reality we might only have some small incremental changes. And at the same time, what about queries on real-time data? What about the batch and stream unification, the promise we have been making in the industry? And if you think about at the end of the day, Kafka topics have literally zero business value. They're just a pipe and intermediate redundant storage that you can't actually do nothing with those. So in an ideal world, what we would like is to have all the properties of streaming we had all these years, be able to combine those properties with what we know about data warehousing in the lakehouses, like how to query all the data we need, and how we can also there have things like a key value store or a cache. And this is our contributions here, like, hey, have you met Apache Fluss? And this is the funny part, because the previous presentation had dogs, this presentation has otters. So I like the diversity in terms of animals. So with Fluss, we are doing a simple thing, and we are basically introducing streams as queryable tables, which is also what data analytics are familiar with, and what makes sense there. It's as simple as that. And with just this simple solution, we move from topics and partitions to actually tables and buckets. Because so basically, there's the Kafka topic that has partitions, and the tables have buckets that provide the exact same functionality and ensure strict ownership guarantees similar to Kafka partitions. And Fluss also has partitions, but it's partitions similar to databases, where you can partition by date or by user ID, for example, to further speed up your analytical queries downstream. And it comes with two flavors. We have the log tables, as we call them, which provide the exactly same functionality like Kafka, but along with that, we also have the primary key tables for keys and handling updates. And all of that is based on the Apache Arrow IPC streaming format, which is also what brings columnar streaming directly into Apache Fluss and allows us to have all these, let's say, data warehousing properties. So with all these components, it's like we are creating a new streaming database and how we see things in the modern era. And just these foundations, and basically we end up with a simplified architecture with something like this, where you have the ingestion, the Fluss cluster with the distributed log and cache, offloads into the Lakehouse, and you get all these benefits. And we'll see the next in detail one by one. And because we have tables, we easily solve the first of our two sins. And the first sin is in the ability to query data streams. So with Kafka topics, because they're just used as a pipe, you can't look up your data, you're unable to debug your data, you are unable to fix data errors. You have to offload the data somewhere, do backfills, all these kind of scenarios that, especially at scale, this become a pain point. But now instead with Fluss, we can look up our data, we can debug our data, and fix data errors within our data. The second part is the schema enforcement. And because we are playing with tables here, we have direct schema enforcement. And the other cool part with Fluss is that all these schemas actually get synced directly from the real-time layer on Fluss directly onto the historical layer, which is the Lakehouse, and we have direct metadata syncing. Now, moving to the third sin, the lack of changelogs. So what is the changelog? Kafka is an immutable event log, so this means it can't reason about keys and doesn't know about the updates. When downstream engines like Apache Fluss need to perform aggregations or streaming joins or whatever, all these operations actually operate on keys. Now, because Kafka is unaware of this concept, you can think actually of the changelog similar to the database, right? We have the database table, right? And we also have the append ahead log or bin log or whatever you're calling in the database. Every time a change happens on my database primary key table, it is reflected on that wall, and it's also used for recovery in terms of failure, and it is similar. So Flink needs to generate the changelog because Kafka doesn't, and this means that even if you have the same topic and you want to reconsume it again and again, you duplicate all the data from Kafka on Flink, and all this state lives on Flink state. Now, Fluss generates changelogs, so you just have it there once. You don't need to duplicate the storage, and as you can see from the streaming benchmarks, it can reduce the total, you can cut the processing time almost to half just by not producing the changelog, and can remove it can reduce the state up to 1/3. Like from 1 terabyte, you can see here it's 350 gigabytes. So this is just because of the changelog. The next one is the separation of a log and a cache. So when we are running distributed systems, we often need to maintain both a distributed log and a cache. And one of the hardest problems in this architecture can be the cache invalidation. Data usually flows first into the log, and only afterwards is the cache updated. And as you can see here, this creates timing windows where the cache might be stale. And teams typically try to pass these things with TTLs or background refresh processes or change data capture updates, but none of these actually solves for this problem. Staleness is just part of life when you split log and caches. Then we also have all the burden of having to maintain dual systems like both a log and a cache, and you also run into things like dual writes, into issues with dual writes and atomicity, and then you need to be careful and orchestrate carefully with things like outbox patterns and distributed transactions. So what Fluss provides, as we said, is the primary key table, and this is what merges both. You can get both into the same systems, and this is what enforces also the concept of stream and table duality. Every change that is going to happen, basically on the key value store, is first added into a pre-write buffer. It gets persisted to the store, the log store, and then it gets flushed into the key value store. So basically, we don't have any issues anymore with caching validation scenarios. We don't have to worry about dual writes. And the most important thing is we don't have to maintain different systems. We don't need to maintain an external key value store or a cache. The next thing is the network data transfer costs. And the question here is, how do you query only the data you need so you don't spend redundant you don't get fat bills by just querying redundant data. You don't even need at the end of the day, like you don't have to transmit all the data just to filter it on the client side. And the first thing that Fluss allows, because it allows partitioning, is to only read the data from specific partitions. So let's say, for example, you only need to read the data from the last day or the last month or whatever. By using proper partitioning with Fluss, you can achieve that. You're only going to read the data from the appropriate partition, and that's it. And basically, from our benchmarks, when you're writing to partition tables, on the right side, the performance is pretty much similar. It doesn't have much difference. But as you can see, in the network traffic and the read time, we get the network traffic gets reduced by up to 20% when using good partitioning, and at the same time, our reading time is also reduced like a lot. And this is just from partitioning. The second one is the column pruning technique. And this is, okay, let's assume I have a payload that contains hundreds of columns. But in reality, if you think about it, when you're doing aggregations, you need like 4, 5, 10 at best, which means all the other columns are transmitted for no reason, just to go to waste and be filtered onto the client side. So Fluss allows column pruning, and also because it's based on partition on Apache Arrow, it provides zero copy data transmission. And especially when we're pruning, let's say, most of the columns, you can see we also get like a 10% improvement in throughput compared, let's say, with Kafka, while also reducing our networking costs. And the final one, which is one of my favorites, but unfortunately it's going to come in the next release. The work is already there. We just didn't have enough time to merge it, is the predicate pushdown. And basically, in Fluss, you can create predicates, and the agent will push them down. It would evaluate filters using indexing and file statistics, and then it's only going to find the right matches and just return the data you need, nothing more. So you can realize that if we apply all these patterns together, how much we can actually reduce our networking costs and literally only query the data we need and not redundant data. And especially at scale, this problem becomes extremely important. The next scene is what I like to call the curse of streaming joins, and I use the curse of streaming joins because they are really interesting in the sense that they are one of the biggest challenges and at the same time one of the most important use cases in the streaming processing space. And imagine, for example, having to do multi-table streaming joins, like 10 plus tables and topics. Typically you result with having state, which is expensive and redundant. You need to configure TTL to control your state sizes. It's hard to perform data correction, and overall, the more it scales and the more tables you add, it starts resulting in poor scalability as well as performance. With Fluss, we are also introducing the era of zero-state streaming joins. And zero-state streaming joins doesn't actually mean they're stateless. We are just removing the state outside of the streaming operators directly onto the streaming storage, where data can actually live, be actually useful, be reused from any edgings, and remove all the pressure on the stream processor. And the first technique there is partial updates. And the idea here is you have multiple streams you want to merge together based on some primary key. And typically, when each stream arrives here, it's going to update its respective columns and nothing more. And at the end of the day, when all streams will have arrived, you will have your final output. The next one is streaming lookup joins, and here you can use a stream and dimension table to perform really fast queries per second for dimension joins. And the most exciting feature that Fluss provides is the delta join. It's about stream-to-stream join, and instead of using Kafka and using Fluss, you don't have to maintain large states on the operator. Instead, you create indexes and perform lookups on these indexes. And from the first production use cases, we have seen that it has removed the need for 100 terabytes of state, all those eliminated. The checkpointing time went from 90 seconds to just 1 second. Overall, compared to Kafka, it resulted in 85% lower CPU and memory costs. And because now you don't have your state on the stateful stream operators, you can do fast updates without having to bootstrap state, which can be really time-consuming. And finally, of course, because it's there, it's queryable, you can use and you can query the results with the Fluss APIs in real time. Our last thing that I'm not going to touch a lot, because there is an amazing talk coming after me that goes into depth around it from the original creator of Fluss, is the separation of stream and lakehouse. And this is what we saw before, that basically we are differentiating between streaming and a lakehouse. But instead, with Fluss, we get one layer. You have Fluss as the whole tiering, and basically all your data gets offloaded into tier storage based on lake format tables. And right now it supports Pymon, it supports Iceberg and Lance. Lance is a new format for multimodal data and AI, for those that are not familiar, and allows the ingestion of text, videos, these kind of things, generate actually vectors, and that works really well with vector search. We have our real-time data, our historical data being coexisted together. And the other great part is that because actually Fluss has the concept of partitions and bucketing, the zero-copy data is actually analytical ready, because the lake formats are going to share the same options there. And with that, another interesting thing is what we call the union reads, which allows you to run queries, and they will combine both historical and real-time data. So when you run a union read on Fluss, you actually have your historical data being read on the Lakehouse, then you have your streaming data being consumed, and the query result will merge both and will provide a complete view of both historical and real-time data. So, this is what I had to say to you. I hope this was interesting and exciting. And if you like what you saw here today, I have a big favor to ask. After this slide, because I had forgotten I had this slide, these are the key takeaways here. So basically, we have streams as queryable tables. We have the changelogs that keep track of all the changes that take place. We unify the distributed log and the cache based on the primary key tables. We only query only the data we need. It's introducing the era of zero-state streaming joins. It reduces the copy of data with zero copy. And finally, architected for the streaming lakehouse unifications. So if you like what you saw today, please, the authors had put me to say this. Take your phones out, scan this QR code, and please give a star on the project on GitHub, as it will help our work a lot. And if you can also share what you saw here with your networks to help share awareness, it will be amazing. Thank you, everyone, for attending my talk. Who loves these authors? When I saw this from AI, I was like, I really need to add this in the slides.
Thank you. I have a question about the Kafka compatibility support. I know you're working on that, and I'm just curious because Kafka, as you said, doesn't have schema; it's just a binary storage. I'm sure it's real challenging to make sure it works seamlessly. So maybe you can share more about the challenges and some of the learnings of that.
So actually, I would like us to talk more about this after this talk. So here's the thing: we have the Kafka compatibility on the roadmap, and there is some initial work already there in place, but due to bandwidth, the contributor there hasn't continued and the work is stale basically at the moment. Now, this is my personal view, not on the communities. I'm trying right now to figure out if the Kafka compatibility makes sense for two reasons. The first reason is that the main use of the Kafka compatibility is for easy migration, if someone wants to migrate from Kafka to Fluss, let's say. However, as you have seen, Fluss provides so much more than Kafka in terms of API. So at the end of the day, it will be just about writing messages. It can't actually leverage all this functionality that Fluss provides. So I'm trying to figure out right now if it actually makes sense to provide the Kafka compatible API, or it's better. I mean, if anyone in the community wants to do it, I will be glad to support it. But considering there are so many more interesting features of priority, this is something I'm trying to figure out. And we try to work with community feedback. We got tasks, but it's more about, we don't get concrete production asks, let's say. So I guess it remains to be seen. But if you have any thoughts about it, I would love to talk more. Anyone else here wants a Kafka compatible API out of curiosity? The rest of you win. Okay, either I did a really good job explaining everything. Yeah.
For your scene number 3, I wanted to ask if you also considered yes, for this one, did you also consider when you did the benchmark about the log compaction that Kafka also provides?
The log compaction, I don't understand what do you mean, how is it relevant?
You said to get the latest values from your keys. So Kafka also provides.
So Kafka does provide log compaction, but this log compaction is basically a cleanup mechanism, and it doesn't enforce updates on the latest keys. When it's doing this compaction, it doesn't give you the latest key. It gives you at least the latest key. So it means you can have both. And even if you did this, it doesn't solve the problem because it can reason with updates. Even if you keep the last value, it's even worse. Because if you read that value, you don't know what, I mean, you read the value of 4. Before, was it a 3 and I need to add 1? Or it was a 5 and I need to remove 1 from there? You see, this is something tricky to do, and doesn't work like that. Yes.
I have 2 questions. I'm not sure if we have enough time, so I'll start with the first one. Like, what is the maturity of this technology, and like, how confident can we be with like replacing Kafka with this one? Like, if are there already companies that running large production?
And I will also leave this question also for later to Jark, who is the creator of Fluss behind there, and he's hiding right now. I will put you in the spot in a bit. But Fluss has been running in production environments for almost a year now. Its maturity has been proven. What is difficult right now, because we also need to say the hard truth, not only the good parts, is that on the open source, we're just releasing Helm charts to help our users deploy in Kubernetes, but this will need more, let's say, it will need some more love from the community to help us grow them more mature. So in terms of open source deployment, it's more on the early days, but in terms of the product actually running production, it's battle tested at terabytes of data in quite a few environments. And we also have one, because of the nature of the customers, it's really hard to get the use cases out. We already have one, it's also on the website, from the largest e-commerce in China. And it's about recommendations how they use Fluss, and there are more that will be coming soon.
Thank you. And the second question is, in Unity, we have like a data platform that we are using Flink to read from payment and then write to payment. And we also look at it as kind of, not, I wouldn't say queryable Kafka, but like it gives us pretty like short latency if we are reading and writing for payment. And like, I'm not sure I really understood. I mean, the exactly like when Fluss can replace Kafka and when it can replace Payman.
This is a great question. First of all, thank you so much for using Payman. I didn't know that Unity was using it. It's amazing. Please share your story. And the second part, and the important, because also Pymon was created for low latency, right? But it's more about near real-time latency. So if your use cases can afford near real-time latencies, at least to the minute level, then whether it's Kafka or Fluss, you don't have to pay the extra cost of that low latency infrastructure actually requires. So you can go directly with Flink and Pymon. But if you actually need low latency, this is where Fluss comes in. So the ones for it to handle for really low latency, really low latencies, like Kafka, and the other one is that for near real time latencies that don't need that cost, so you get more cost-efficient solutions with that. Yes.
There is another question here from Unity.
Hi. So question is, does Fluss provide like an online store? Like if I have millions of requests of key value lookups, can we do it with Fluss?
Yes. And I think, Jack, you also had some numbers there. You could ask him later. I will put him in the spot a bit. But yeah, it has, I think it was 500 million. Oh, okay, I'm not going to say the wrong numbers. I will let, because I don't remember it on top of my head, but there are previous presentations around that had concrete numbers and how many queries per second the largest tables have been able to sustain so far.
Thank you.
I think it should be like 500,000 per second, but with a question mark. I need to verify the number. Yeah. So, thank you all for joining my talk.
Hey, Yanis, nice presentation. Good work. My question is basically around, you mentioned schema evolution. So because Fluss supports like internal and external tiering, so I can imagine that sometimes data can be inconsistent between because until the next compaction is run, until the next snapshot is generated. So how to deal with it and how Fluss currently handles this?
So basically, the idea is that all these things go through Fluss. And basically, the way it works, and actually, the schema evolution is another thing I didn't mention, is work that is in progress, that is also coming in the next release. And I will also let Zark expand on that, because it actually provides a concept of zero schema evolution. And basically, the way it works is that you get your tables on Fluss, you update the schemas there, and all the schema changes actually get propagated directly on the data lakehouse. Now, if you run compactions and all these things, the schema doesn't make any difference. I mean, on the schema side, unless I'm missing something. Yeah, thank you all.